Okay, we want to spend some time talking about bonds. And the main reason we want to set this up is because we ultimately want to talk about reactions. Not today, but we want to set up that conversation. Reactions will have a view about them where they are essentially going to be elements and compounds combining and making new elements and compounds. So it's really important to see how things combine. We can have two general compounds here to take a look at in the beginning. I want to look at sodium chloride, and I will also look at something like HF or HCl. Two general classifications are going to be elements that transfer electrons and elements that will combine and share electrons. So two broad categories. There are some other things that we will need to know, like electronegativities. And remember, the electronegativities were essentially a numerical value that showed how much an element wanted electrons. And we know that fluorine was way over here, really wanted electrons, and francium was way down here and really didn't want electrons. So essentially, things on the right side of the periodic table have higher electronegativity values than things on the left. We also know that that trend increases like this as you go up and as you go across. So that's just a quick review. So let's take a look. When we look at this, I'm going to erase this real fast. When we look at all these things here, we're going to have four types of bonding. We're going to have ionic and covalent, which I said is our main focus. But we do want to mention that there are metallic bonding and also molecular bonding that occurs. So metallic bonding, just to get this out of the way, is going to be more of an advanced placement type thing, but this helps to describe how metals get their behavior of conductivity. And in this case, electron is free to move around the nuclei of metals. So things like electrical conductivity would be easier to explain here because electrons can move in and around all of the atoms of a metal. On the other hand, molecular bonding, where is a situation like in diamonds, so a good example is diamonds, and the substance actually acts like a large covalent molecule. It's so big, and all those bonds end up supporting each other and usually have very high melting and boiling points, so they're very, very strong. So elements get together and they form chemical bonds, and we're really going to focus on ionic and covalent. The two differences are easily distinguishable if we study the electronegativity differences. Here's the key. If you understand the electronegativity differences, you will be able to predict if something will form an ionic bond or a covalent bond. So let's look at ionic bonds. Ionic bonds are usually formed when the electronegativity is greater than 2.0. So in our example, sodium and chlorine, if we went to the periodic table that we have in our book that shows some electronegativity values, we would see electronegativity values of 0.9 for sodium and a value of 3.0 for chlorine. The change in, or the difference in electronegativity in this case is equal to 2.1. Thus, this would be a type of compound that would be formed by transferring the electron. As you can see here, we have an electron that was present and it's being transferred here to the chlorine. We end up having sodium ion positive and chloride ion negative. This positive and negative attraction is a very strong force making the compound sodium chloride. This is an electrostatic form of attraction where opposites attract. So positive ions, cations, are being attracted to anions. And it's because the electrons have been transferred. Some characteristics, yes, they are oppositely charged. Sometimes we have multiple things, like when we have calcium, which is +2, we could have 2 chlorides being attracted. This forms a very stable compound. In fact, that is the main reason elements even do combine to make bonds and make compounds, is because they are more stable in this arrangement. They are actually taken or transferred, the electrons are. Covalent bonds, on the other hand, are formed because the elements involved are more stable if they share electrons. So in this case, we see silicon is a giant molecule. They're sharing electrons all over the place. This would be an example of that network or that molecular bonding, but it's like a network solid that forms, and it becomes a giant molecule. Another example would be something like HCl, and in this case, if we go look up electronegativities, we have 3.0 for Cl, and we have 2.1 for hydrogen. The change in electronegativity is going to be 0.9. This would suggest that we are below that 2.0 threshold, so electrons are being shared. If they are being shared, they sometimes are not shared equally. If they are shared like this case of 0.9, it's a relatively high number for sharing of electrons, so it's not a very good sharing, they would be considered polar. If we had something like hydrogen with itself, well, this change in electronegativity is 0. So this is a non-polar sharing and a non-polar covalent molecule. So key parts: if you are polar, then you're not sharing electrons equally, but you are still sharing. If you are sharing them relatively equally, sometimes 0.5 is the break point here, not necessarily 0 like we just showed in that example, then you are considered a non-polar. So polar are between the 0.5 and like 1.7 or all the way up to that 1.92 range. They're shared unequally. This would be shown with poles, like we do have a north and a south pole, or we do have a positive pole and a negative pole. We do not put positives and negatives in this format alone. We will actually use that delta symbol, which is the Greek symbol here, as meaning partial positive and partial negative. Very different than ionics, so that's why we have to show that delta symbol, that's a lowercase d. Nonpolar covalents are below that threshold of 0.5. Okay, electronegativity and bond type is what we need to get comfortable at, or comfortable with. This is an example here, and I have 3 compounds, or 3 bonds to consider: magnesium chloride, calcium chloride, and strontium chloride. The compounds that are actually formed would be SrCl2, CaCl2. This is good because all the ice on our streets, this is what they put on the streets to melt that ice. And MgCl2 all have this kind of arrangement. Notice though, when we make the decision about bond determination, we only use one of the chlorines. So we would, for example, instead of saying magnesium, and this bond, chlorine and chlorine, we're only going to answer for one bond, and we will therefore classify the object or the compound as ionic or covalent. In this case, we go look up electronegativities from a chart like this, and we see that magnesium chloride will be 3.16 minus the change in electronegativity, 1.31. This value is 1.85. And if we did calcium chloride, we'd have that 3.16, and then we would have calcium's 1.0, and the value would be 2.16. And then finally, strontium and chlorine. Notice that the chlorine is always right here. It doesn't necessarily have to be first. You can always take the absolute value of these. You should never have negative numbers. They're always going to be absolute value of the electronegativity. You just want to know the difference. This is 3.16 minus strontium's 0.95. So when we look at these, if we were ranking them into short, long, ionic, and most ionic, we would show that the strontium chloride is the most ionic, shortly followed by the calcium chloride. And then the magnesium chloride would be considered polar covalent because its difference is only 1.85. If we were talking about how close or long these bonds are, then the longest would be closer to, would be a larger number. So 3, 2, 1 would be the ranking. Okay, that's what I have for you today. I hope that you are able to get some notes from this. And this should set up our ability to start talking about when magnesium, for example, reacts with chlorine to make magnesium chloride. Please understand I did not balance. Well, this reaction is balanced, but in some cases I would need to balance. Another topic for another day.